question is, if there is no charges to flow, will there be a charge?
Okay, let's go on YouTube, and then I will try to reply to this question. Okay.
Question is, if there is no charges to...
Okay, that should be, right now we should be live, and I'm back. Okay. So we talk, Ernest's question, let me see it. So,
but, Professor, this question is not very clear. If there is no charge flow, will be there a charge? So what does it mean?
Okay, so let's go with the continuity equation. That I'm repeating, the continuity equation is not something new that you get it. So it's something which people, they get it from Maxwell equations. Okay, just to clarify this. And we take the divergence, we took the divergence of curl of H. And then from this, what we will get, we got the divergence of J, and other side, well, I don't memorize things, so I have to drive it again. So curl of B was equal to mu zero J plus mu zero epsilon zero time derivative of E. Okay. So, and then we took the divergence on both sides. So divergence of a curl of B, and then we had mu zero divergence of J, and then we had plus mu zero epsilon zero divergence of a time derivative of electric field. We stated the time derivative can be swapped with the divergence. Then I will get divergence of E. Here we replace it by rho divided by epsilon naught, and curl of B was equal to, the divergence of curl was 0. And then we got 0 equal to mu 0 divergence of J plus mu 0. Epsilon 0 goes away, and then we had the time derivative of rho. Okay. And then mu 0 is not equal to 0, then we get divergence of J plus time derivative of rho respect to time derivative of rho equal to 0. So what I say, so let's pay attention to J. What is J? Is the current density. What is rho? Is the charge density. Today, you will see that I have to do the integral on a volume in order to give it, to provide a meaning to it. So, well, if you assume a region, which is a volume, then you have a certain charge distribution inside. So it means that the total charge inside is fixed, there is a total charge, then you have a current which is coming in, so that's a current which is coming in or maybe going out from this region. So and that's what I call it J. Okay, so what happens if rho, the charge, the amount of the charge density, is not a function of the time? So it means that Q at any given time is fixed. It has a fixed quantity. So the total charge inside of this volume is a fixed quantity. Then what you expect, any current that is coming in, it will go out. So if you add, for example, one charge inside, definitely there will be another charge going outside. Okay. So this is the meaning of the continuity equation. Unless the charge distribution is changing upon the time. So if you have, again, the same volume, so if you add more charges in, okay, let's say Q1, Q2, and etc., Q3, then what you expect that the charge density inside of these also will change. upon the time. So what does it mean? So I'm not expecting that in this volume, the charge appears by itself. So it should come either from outside of the region, or the in total charges inside of these should be a fixed quantity. This is the meaning of the continuity equation. Is that clear, Ernest? Can you type in Q&A? Okay. Fantastic. So we will go, maybe I will discuss these when we introduce the Gauss theorem, but yeah, okay, perfect. Thank you. So let's go with the integral formalism. So yesterday we stopped when we say that, well, we have a scalar quantity, the scalar quantity of phi, which was x, y, and z. And then we say that we have infinitely small displacement of dr, which was the vector of x dx plus y dy plus z dz in a three-dimensional space. And we say that how many ways of creating integrals one can end up with. So the first form was easy, was taking this scalar quantity of x, y, and z, multiplied by dr. You can do it, of course, dr is a infinitely small displacement of r. So it means that you either you move in a three-dimensional space or on a specific trajectory, and dr is the infinitely small vector that you have it in this direction. And you start from a point of A and you end up in a point of B. Okay, so it means that you have RA and then you end up, in RB. Okay, or what you can do, you can have this scalar quantity, you take the gradient of this. Or let's go with the general formalism. Oh yeah, let's go. That dr is one form. Or in general, you may have also a vector of v, which is a function of x, y, and z. And then you do integral of vector of x, y, z. Either you will do it with a dot product of dr, or you will do with a cross product of dr. These are the other forms that someone may face. And we went with an example. We say that let's go with the second part because, well, the third part also is clear. The result is a vector. The first one now is a scalar quantity. And the example that we looked into that was work, which work is given by f dot dr. Okay. And we reviewed that. And finally, we say, well, let's go with not integral on a line, but integral on a surface. Integrate on a surface. And I say that, well, surface, of course, it can be a scalar quantity, but the surface that I'm considering here is a vector quantity, which has a unit vector, which I show it like this, or I will write it as a d sigma. And what is the definition of this? I say, well, you should have, you can have either a closed surface, which means that you have a volume inside. And usually closed surface, we show it either with S or we show it derivative of volume in general, okay? So that's a definition showing that this is a surface. If there is a question, please let me know. And usually when we go in n-dimensional, we introduce derivative or partial derivative of volume. Well, if you take a volume, the surface is given essentially by derivative of a volume, okay? Or you can show it either with the surface of S. So what is going on with element of surface? We say that the element of the surface has the magnitude, which the magnitude is given by dA, infinitely small, let's say, surface, but the unit vector, which is not a constant, remember, n is not a constant, is for a closed surface is towards outside, okay? So if that's the volume is embedded inside, the unit vector orthogonal to the surface is always outward, okay? And that's the direction of n. And n, remember, is normal to the surface. Here is this, here is this, here is this. You may have the same dA, but n is a function of coordinate. So n is not constant, okay? So then now I have a unit vector, which is introducing, or let's say infinitely small surface, which is introducing the surface vector. Now the question is that how many forms of integral I may have. So the first form is, again, with a scalar. You can have a scalar of phi, x, y, and z, and then you multiply by d sigma. Either you will do it on an open surface, or you will do it on a closed surface. Phi, x, y, z, d sigma. So the first term is a scalar, the second term is a vector. So the result of these is a vector quantity. What is the second option? The second option is that no, you will take a vector of x, y, and z. Then you will do a dot product with element of the surface, d sigma. Either you will do it on an open surface, or you will do it on a closed surface, x, y, z, that d sigma. And the result of this is a scalar quantity. And finally, the third one is that you will take a vector of x, y, and z. You will do a cross product with element of the surface, again on an open surface or on a closed surface. D sigma on a closed surface, this is a vector quantity. Okay, so those are really, really important vectors to be calculated. So let's go with the first example. Take the first example. You can do it with an open surface, or you can do it with a closed surface. It's up to you. And the result of these essentially will be phi of x, y, and z. Then d sigma, essentially, as we say, that is x hat d sigma x plus y hat d sigma y plus z hat d sigma z. And then that becomes three integrals indeed. So it will be integral of phi x, y, and z d sigma x plus y hat integral of phi x, y, z d sigma y, and plus z hat integral of phi x, y, z d sigma z. We will do a calculation about that, okay? However, we have the second form. So that, of course, you need to know the phi x, y, z, and also the d sigma, and then, of course, the surface that you are taking the integral, and then the result of these can be calculated. We will do that for one example. The second example, which is important also, is integral of a vector dot d sigma. So the result of these will be integral of Vx d sigma x plus Vy d sigma y plus Vz d sigma z. Okay, and that's on a surface. So indeed, that also becomes t integrals, Vx, x, y, and z, d sigma x plus integral of Vy, x, y, z, d sigma y, and integral of Vz of x, y, z, d sigma z. Okay, this is the most common integral, most common surface integral in physics.
Sorry, Professor Karimi, you have two questions.
Yes.
First, Baran asked, what's open surface?
Okay, let's go with an open surface. I told that I introduced that in the past lecture. So, if you, the closed surface is clear, right? So if you have a volume, then this surface is closed, and we say that is given by this, and then normal to this surface is the n, which we are dealing with. Okay. Now let's go, and that's a closed surface, which is creating a volume. What is happening with an open surface? Assuming that you have something like this, okay, is a circle. Now, this can be a surface, or this is a surface that you have it. But the surface is not creating a volume, does not create a volume. The way that we introduce normal to the surface, of course, that has an element here, so I call it dA. But what is going on with the normal to the surface? If you do the integral on a loop such a way that, for example, the orientation is going counterclockwise, okay, then the normal to the surface will be like this. And then d sigma will be introduced as nda. Okay, and that's a positive direction that we have. That surface, for example, you can create something like that people they're creating soap bubble. So they usually what they have a ring, right? They place it inside the water and soap, and then on the other side you are creating a surface, right? That's true. And now this surface has a hole, and where is the hole? Is here, because that's air that is going inside. We call this also an open surface. Good. Is there any other question?
Another question is, why do the open surface is not written del V?
Open surface is not written del of V. Why I should write it as a del of V? I don't get that. Del of V is a vector. Okay, but V is a volume. Is a volume or the vector's component? I don't understand that. You may write it maybe in a different way. No other question?
No, for now is all.
Okay, wonderful. So remember that this integral, which is the integral of the v dot sigma d sigma, is the most common integral in including the involving the surface, appears in physics. So the third example, well, I'm just writing down, but well, we may not use it at all, is it was integral of v x y z cross d sigma. And well, what we have to do, that is also the result is integral, but it has several components. So I mean, it has three components with several form of calculation. So if you calculate the x component, that will be v z d sigma y minus v y d sigma z. So that's the x component of that. Then we have another one, which is y hat, integral of, let's go this way, v z d sigma x minus v x d sigma z. And finally, we have a z hat, integral of vx d sigma y minus vy d sigma z. So remember, each of them, they are integral on a surface, each of these. So we have 6 integrals on surface. So we introduced the integral on a line, we introduced integral on a surface, and now we are going with introducing integral on volume. Integrating on volume. So volume, the definition that we have, I mean, the notation that we use, usually you go with a d tau, or you go with a dv, which is the symbol for the element of the volume. Okay, and in Cartesian coordinate, that is dx, dy, dz. And it can also be introduced in curved space. So either you have a scalar of x, y, and z, you integrate it on a volume. The result is a scalar. Or you may have a vector of v, x, y, and z integrating on a volume, which is a vector. And no other options. So we have 2 easy integrals, very, very trivial, that we have to solve. So essentially, the first one will be only one simple integral of a multi-parameter, which is dx, dy, dz. And the second one is a vector integral, means that you have 3 components integrating on dx, dy, dz. So and easily we can do the calculation. So yes, that is x. Thank you. Thank you very much. Good, lovely. So well, now from the derivatives, which they were gradient, divergence, curl, now we move to the integral formalism. We introduce let's say 8 integrals. One was the integral of a scalar quantity on a line, integral of let's say a vector dot the dr, or v cross dr, or we did it with the surface element as well, which was another 3 integrals, or we do it with volume, which was either a scalar quantity or a vector quantity. Okay, so this is so far clear. But what are the relationship of these integrals with the gradient, with the curl that we previously introduced them? So gradient of phi indeed can be also written as an integral formalism. It can be written as a limit of integral of phi, okay, d sigma divided by integral of the volume when the volume goes to be tending to be 0. So what I'm doing here, we are linking derivatives, which they were gradients, divergence, or whatever, to integral on surface. Okay? So let's prove this. Let's see if really that identity that we introduced, that the gradient is indeed given by integral on a surface, is true. So let's do a simple function. You have a function of x, y, and z, and again the continuity should be fulfilled, or let's say being well-behaved function. And then I want to calculate this integral on a surface, and this function on a surface of d sigma. Okay, so I want to calculate the following integral. So when we talk about d sigma, it seems that we are dealing, let's say, with a closed surface. Let's go with a closed surface or a volume. So I'm considering a volume, which this element is dz, this one is dx, and this one is dy. Okay, so what is the volume of this? Is dx, dy, dz. How many surfaces do we have? We have one on the back, we have the second one on the front, we have the third one on this side, we have the fourth on this one, we have the fifth on the lower part, and we have the sixth on the top. It looks like a dice. Is the screen visible?
Yes, it's visible and very good, no problem.
Okay, wonderful. So I want to calculate the phi d sigma for this volume. Okay, is your choice to choose the coordinate. So the coordinate that I'm choosing is like that. I will keep it at the middle. Okay. So what does it mean? That only looking at this surface one, this is the distance is dx divided by 2. If I look at the back surface, is minus dx divided by 2. Okay, is a choice that you do have. For simplicity, we will do this. Okay, and then for the other direction is minus dy divided by 2, and here is dy divided by 2 until here, and the same here is dz divided by 2, and the lower part is minus dz divided by 2. Now I will write it down in a different form just to make it more easy to be understand. So we have 6 surfaces, and what I have to do, I have to do the calculation of phi x, y, z, and d sigma for the surface 1, plus integral of for the surface 2, the same for surface 3, the same for surface 4, and until phi d sigma for the surface 6. Do you agree, guys? Is there any question?
Yes, we have some questions.
Yeah.
First, how one can interpret such a construction as a integral by surface over the vector product with the normal.
How one can interpret such constructions as an integral by surface or the vector product. We will see that, yes. I will introduce that as well.
Another question is, when you do the cross product, is there any difference whether the function is integration or derivative? I mean, do we use the same rule?
When you do the cross product, is there any difference whether the function is integration or derivative? When in derivative, you have to be very careful, because if the cross has the operator, it should act on the function. And for the integral, no, is a normal integral that we have to do.
Another question, how we can say this type on integrals to an operator? I mean, the math that linking them together, and also a physical explanation for them.
Yeah, wait for it. Okay. Yeah, wait for this. You will see in a few minutes. So what is the linking or the physics that links the two together? Okay. So we have the integral of phi x y z on d sigma on six different surfaces: surface 1, surface 2, surface 3, surface until surface 6. So, well, what is the value of the function on the surface 1? On the surface 1 means that the front surface. Can someone tell me? You can type it. So what is the value of this? So that was the origin, and the distance of the surface from the origin was dx divided by 2. Okay. What is the value of phi here? No, phi. I mean, I'm not talking about the d sigma. What is the value of the function? The function of x, y, and z should be introduced here, right? Should be on this surface. What is the coordinate of that surface? That's x direction. That's a y direction, and that's a z direction. Well, I see Amir Hussein. Partially is correct. Okay. Is not YZ coordinate. Is I'm not asking for that kind of result. I'm asking for the value of phi. Phi should be on this plane. What is the coordinate of this plane? Definitely x for this is dx divided by 2, right? So indeed, for surface 1, phi is given by dx divided by 2 and y and z. Do you agree? Lovely. Okay. That can be any places. Okay, so you can choose also that will be, because approximately for this surface, which is parallel, as some of you say that it is parallel to y and z. So indeed, that is very, very small displacement from the origin. So you can assume also that is given by 0 and 0. Okay, I think we agreed on that. What is happening with the surface 2? Surface 2 was, sorry, I did a mistake between surface 1 and surface 2. So, I think one of you say that is totally correct. Surface 1, in my definition, surface 1 was here in the backside. So that was the surface 1. And surface 1 is given by minus dx divided by 2. You are right. So it was minus dx divided by 2. That is surface 1. And surface 2 is the front one. Surface 2 is the front. And the value of this is dx divided by 2. So essentially for surface 2 is phi of dx divided by 2 and 0 and 0. Agreed? We are not talking about yet about d sigma. D sigmas are, we keep it for the end, okay? We are right now talking only about the function, where the function should be calculated on the surface 1, surface 2, surface 3, 4, and 5, and 6. So we have to calculate those functions, means that they should have a value. So for the surface 3, what are the values? For the surface 3, if you look at this, for the surface 3, it will be phi of 0 minus dy divided by 2 and 0. For surface 4, in the same way, phi of 0, dy divided by 2 and 0. And finally, for the surface 6 will be phi of 0, 0, and dz divided by 2. For surface 5 will be phi of 0, 0, and minus dz divided by 2. Do you agree? If you don't agree, just type it in a chat, in a Q&A. Good. So now we need to calculate d sigma, d sigma, d sigma, and etc. We have 6 d sigma for the 6 surfaces. For surface 1 was this one, right, guys? For surface 1, what is d sigma for this surface? Definitely the direction is negative. Remember, it's a closed surface, right? So normal to the surface is towards outside. So it means that is in minus x direction, right? That's the direct, exactly. Some people, they have written minus dy dz. And what is the value? Here is dz and here is dy. So indeed, that will be minus x dy dz. So we write it down. So here is minus dy dz in the direction of x hat. Do you agree? Good. What about the surface 2? Surface 2 is the front one, is in the direction of x hat, but the value is dy and here is dz. So that will be dy dz x hat. What about surface 3? Surface 3 is the back side. It will be minus y hat dx dz. And surface 4 will be in the direction of the positive, which is this direction, right? Will be y hat dx dz. For surface 5, that will be in the direction of z, but negative, would be minus z hat dx dy, and that one will be positive, sorry, z hat dx dy. So we have all surfaces quantity, and we have also the functions that should be calculated there. So the first one, approximately, because we assume that dx, dy, dz, they are small, okay? Then approximately the result of this will be phi of minus dx divided by 2, 0, 0. Then you have minus dy dz in the x direction. Result of 2, that's for surface 1. The result of surface 2 is plus phi of dx divided by 2, 0, and 0. dy dz x hat. That's the result of surface 2. Okay. The result of surface 3 is plus phi of 0 minus dy divided by 2 and 0. And the unit vector also is minus dx dz in the direction of y hat. Then you have for the surface, that's a surface 3. For surface 4, we have phi of 0 dy divided by 2 and 0. Then we have dx dz y hat. That's for surface 3, surface 4, sorry. And then plus for surface 5, we have phi of 0 minus dz divided by 2. And then we have minus dx dy z hat plus phi of 0 dz divided by 2. And then we have dx dy and z hat. That's for surface 5, surface 6. Good. I think we are okay. Don't forget what we are calculating: integral of phi d sigma on a closed surface, which is created by the volume of dx dy dz. So do you agree that dx dy dz, they are small, right? If they are small, well, the first one, I can use the Taylor expansions. So the first result will be phi at 0, 0, and 0. Then you do the Taylor expansion of that, will be derivative of phi with respect to x, calculated at origin, which is the O, which is the origin that we have it, okay, origin of the coordinate, which is 0, 0, 0, then multiply by dx. Then all of these multiply by, all of these multiply by minus, there is a minus sign here as well, because it's a minus dx, so it will be minus dy dz x hat. Then the second term is you do the Taylor expansion, phi of 0, 0, and 0, plus derivative of phi with respect to x. If you prefer, by the way, you can write this as at origin multiplied by minus sign. And here at origin, multiplied by dx. Then we have dy dz x hat. The same way we can do the calculation for other, which will be at the origin plus derivative of phi. Now the second argument is we have to do the Taylor expansion for it. It will be derivative of with respect to y at origin, and that's divided by 2, by the way, and that will be minus dy divided by 2 minus dx dz y hat plus phi 0, 0, and 0 plus derivative of phi with respect to y at the origin. Then you have dy divided by 2. Then we have dx dy and dx dz y hat. And finally, the last terms will be phi of 0, 0, and 0, which is the derivative of the with respect to the z. So it will be derivative of phi with respect to z at origin. And then we have minus dz divided by 2 minus dx dy z hat plus phi of x, y, phi of 0, 0, and 0, derivative with respect to z at origin, dz divided by 2, dx dy and z hat. Okay, So when we sum them up, remember there is a minus sign here, there is a minus sign here, there is a minus sign here. If you multiply them together, that term will be minus, that will be minus, that will be minus. So indeed, this term can cancel out each other, this term and that term, they cancel out each other. This one and this one also will cancel out each other. So the second term minus multiplied by the minus here will be plus. It will be plus, it will be plus. And finally, what we will get the first derivative of x, okay? Then dx divided by 2 plus dx divided by 2 will be dx. So you will have dx, dy, dz in the x hat direction. The second term will be derivative of phi with respect to y at origin. Then you will get dy, dx, dz in the y hat direction. And finally, you will get derivative of phi with respect to z at origin, and then you will have dz, dx, dy, z hat. So indeed, the integral that we had was integral of phi d sigma on the closed surface when dx, dy, dz, they are small, tend to be 0, then is given by derivative of phi with respect to x, x hat, derivative of phi with respect to y, y hat, plus derivative of phi with respect to z, z hat, multiplied by dx, dy, dz, which essentially is the volume. Okay. What is this? Is a gradient. Is a gradient of phi. Where? At the origin. And what is that? Is the volume. And we're supposed to show the volume with integral of d tau, right? So indeed, integral of phi d sigma is equal to gradient of phi integral of d tau. So when integral of d tau tends to be 0. So I can write it in a different form that gradient of phi indeed is equal to integral of phi d sigma and a closed surface divided by integral of d tau when integral of d tau goes to be 0. So, well, now gradient can be linked to integral on a surface, which is wonderful. No, it's not a proof. It's not a proof. Is really an examination of what is happening with the cube. And by the way, the cube that I have considered, the cube was at the origin. You can move it anywhere that you want. So, for example, in this calculation, if you look at this calculation, right, this geometry, I assume that it is located at the origin, but you can move it anywhere. So, for example, you can have your cube located at the center of the cube, by the way, is located at x0, y0, and z0. So all of those expansions that we had, they were expanded around the origin, which was 0, 0, 0, now can be expanded around x0, y0, and z0. So it means that the gradient will be calculated at that point. Okay, so the meaning that we are looking for is that, well, the gradient of a scalar, if you want to calculate the gradient of a scalar, it seems that it look like the integral of that scalar on a surface of a closed volume around the point. So This is the point that you want to calculate the gradient, x0, y0, and z0. What you have to do, it seems that you take a closed surface here. It can be a sphere, it can be whatever, a cylinder. And what you need to do, you need to calculate integral of phi d sigma, and that will give you the gradient of phi at that point, right? D sigma, or the volume d tau. That's the meaning of the gradient, okay? On the other side, remember the gradient was normal to the surface, if you remember that. So we had this discussion in the past. There is, in a similar fashion, I will give it as an exercise to you guys, prove that the divergence of any vector v, okay, is limit of integral of v dot d sigma divided by integral of d tau. Okay, with integral of d tau goes to be 0. The same way, so how to calculate the divergence? Indeed, the divergence of vector is indeed look like the v dot sigma, the second form of the integral that we had it for a volume. You have to calculate the projection of the vector around the normal to the surface, and then you integrate it on the entire of the surface. That will give you what is happening with the divergence. This is really, really important. If you want, I can prove that, but I will give it as an example that you can go home and try to prove these by yourself. Is that okay, guys? Right? If any question, I can do the derivative as well, the derivation of that. Okay. So there is another form which gives you what's going on with the curl. Curl also is given by integral of d sigma. Look at the direction, okay, of A on a closed surface divided by d tau, by the volume. So the meaning also here is that you have to do the cross product of that vector looking at the tangent component of the vector on a surface which is creating a volume, and then what it gives you the curl of that vector, which, remember, if you have a closed surface, the divergence of v means that you have to look at the integral of v, whatever vector did you have it, that product with the normal to the surface, and then I call it Vn, and then you do the integration on the entire of the surface. That gives you a divergence of v times the volume. Okay. While what's happened for the curl, if you have this volume, you have normal to the surface, then what you have to do, you have to do v cross, let's say n cross v, and then you look at the tangent to that one, okay? And then if you do the summation of all of them, they will give you the curl of v times the volume. That's the meaning for divergence and for the curl, which they are really important, okay? Any question? No? Okay. So let's go with, I'm using the second formula which we had, which was the divergence of v. And by the way, try to use exactly the same form that I did. You consider a cube with dx, dy, dz, which is located somewhere in space. And then you calculate what's going on with integral of v dot d sigma and doing the Taylor expansions, and there from that point, you calculate what's going on with the divergence of V, okay? You can obtain this. So indeed, I can tell you that that will be the result, dy dz, which I call it d tau. Approximately, that is equal to integral of V dot d sigma, okay? When dx, dy, and dz, they tend to be 0. Would you please give me just 2 minutes to get a glass of water? I will be back in one minute. Okay. I'm sorry. So if you assume a small volume of dy, dx, and dz, then we just say that, well, this is the identity that you will get it. So indeed, the summation of all, let's say, the summation of all surface, if you do the projection of V on d sigma, it will give you such a result, okay? Do you agree that that is true for the object one? Okay, so for the object one, we have this. Now I'm assuming that I have another object just next to it. Okay, that's another object that I have. So, well, I will consider this to be d, oh, yeah, let's go with that one, dy prime. And that region also is dx, and the height also is dz. So is just attached to each other. It look like two blocks that you keep them together. Okay, they have the same surface and the same dimension for simplicity. I call it object 2. Do you agree that for also object 2, we have the summation of V that d sigma is equal to divergence of V, dx, dy, and dz. Do you agree on that as well? If you write it in the Q&A. Okay. Now, assuming that we have a bigger volume, right? Now is a bigger volume. I am considering both of them together. What is the volume? Is dz, here is dx, and here is, oh, let's call it dy for simplicity. Okay, here will be 2 dy. So the volume that you have it here is dx, dy, dz with a factor of 2, because the volume has been increased. So what happens if I sum them these two together? So the divergence of V, again, will be calculated, but not in a volume of dx, dy, dz, but it will be in a volume of 2 dx, dy, dz, which is the new volume that I'm dealing with. That's a new d tau. What is happening with the surfaces? So the surface, the front, right? The front becomes 2, the back also becomes a 2 factor of 2. the up also will become a factor of 2, the down also becomes a factor of 2. So we have no problem. Essentially, we have instead we have another 6 surfaces, which is those 6 surfaces indeed. But the problem is, or let's say the point that we have to be careful is the place that they attach to each other, right? So this is the place that these 2 blocks, they are kept together. So for one of them, let's say for the right side, d sigma will be like that. And the vector v also is like this. Okay, it's any arbitrary vector. But for the left side, for the green cube, d sigma is opposite direction, but is exactly the same vector of v. So what happens with integral of v dot d sigma for the green surface, and what happens with integral of v dot d sigma for the black surface, because we have to sum them up together. Since d sigma of green and d sigma of the red, they're opposite direction, then they show up with a negative sign. So means that the integral on the surface of the red and the green, they will cancel out each other. So indeed, the sum of the 2 will be reduced to v dot d sigma on a bigger volume that we do have on these 6 surfaces. Is that clear, guys? Is that clear? So we can put another block on the top. We can put another block on the top of the other one, on the side of other one. So indeed, we can have many small segments which they are on the top of each other, next to each other, and look like Legos, which kids, they love it. You can build up an object in the 3-dimensional space. But what is happening for these 3-dimensional space, if you do the integration on each small individuals, it will give you the divergence. If you sum them all together, that will be the sum of v dot d sigma that becomes on the surface that you are creating these objects. And on the other side, that will be divergence of v on the volume that you are creating these objects. So indeed, if you do all of those as summations together, that becomes integral of divergence of v on a volume of d tau, which is the volume of v, which is creating these objects. And the right side will be integral on v dot d sigma, but on the surface, which means that on the surface of the that is created by the volume of v. This is really an important theorem, which we call it Gauche theorem. So what we have done so far, we extended the divergence to a volume. So people usually, what they write it down, they write it in this way: integral, the triple integral of d volume of divergence of v on a volume is equal to integral on a closed surface that this volume is created of v dot d sigma. And remember, that is surface element, and that is volume element. Okay, good. That's the Gauche theorem. All right. So we had another rule. If you remember, when we try to calculate, is there any question, by the way, about the Gauche theorem? You can type in the Q&A. Yeah or no? Okay. If there is no question, we will go to another important theorem, which is really useful. If you remember, when I drive the curl, so what I have done at that time, I say that assuming that you want to calculate v dot dr, which the dr was the elements that we had it in infinitely small displacement here, and we want to calculate the projection of v on dr on a closed loop of a, b, c, d, which we assume that the displacement here was the dx and here it was dy. If you remember, we did this calculation in the past, and what we obtained that curl of v, or curl of v dot d sigma was equal to v dot dr for this closed loop. You remember that we drive these in the past, in past lecture. Explicitly for this case, we say that that results in rotation in this plane. So the rotation is along z direction. So we were expecting that v dr along this loop of a, b, c, d, and going back to a, which is a closed loop, they will give us the curl of v along z direction, and then on the surface, which was dx dy. So that was the result that we obtained. In a similar fashion, we can exactly look like the Gauche theorem. We can consider that you have a loop, okay, which this loop, let's write it in a different way. Assuming that you have a loop, this loop can be divided in infinitely small, let's say, circuits or small loops. Going to the surface, and then I can make the orthogonal lines as well to make some specific mesh, and I can look at only one specific region here, which includes the two of those circuits. So it means that I have one line here, which is going like this way, and I have next to it another line which is going like this way. So again, in the same fashion, I can say that the curl of vector v dot d sigma will be equal to integral, or the summation of v dot dr for that small loop of blue, and the same way for the green one. So it will be v dot dr, and that also will be given by curl of v dot d sigma. And we know that if you do the calculation for v dot dr, so you have to integrate it on path number 1, 2, and 3, 4, and for the green also you have to do the summation of v dot dr for the path number 1, 2, and 3 on the green, and 4, and then if you sum these two together, what is happening, indeed, that small region here, the value of v dot dr will have the opposite signs, so they will cancel out each other. Then indeed, that will be the summation of v dot dr, but on the bigger loop of 1, 2, 3, and 4. So the intermediate one, the let's say the adjacent lines, they will cancel out each other, and that will be the curl of v dot d sigma on a bigger surface or larger surface, which you are creating with that. So if you do these, all of the lines here, let's say this line, they will cancel out on, let's say, clockwise and counterclockwise, and the integration on the two parts. The same will happen for this line as well. The same happen for all of them. So the total result will be this integration from small circuits that you had it here, or loops. It will go to the edges on the object that you are creating the surface with it. It goes to the perimeter of the object. So indeed, the result of this will be integral of curl of v dot d sigma, which is created by this surface, will be integral of v dot dr, which is created by the loop. So that's the loop that you are creating here. This is also very important, and we call it Stokes theorem. Okay. So we have Gauss theorem, which it tells us what is happening with the divergence of a vector v and a volume, which is integral to v dot d sigma. That's a Gauss theorem. And we have Stokes theorem, which it will tell us what is happening with the curl of v d sigma, which is integral to equal to integral of v dot dr, which is Stokes theorem. That is on a surface, and that's on a closed loop. Questions?
There is no question.
Okay, lovely. Yes, Amir Hossein has a point, which is right. He says that it seems that the Gauss theorem brings us from a 3D object into a 2D, which is a surface, and Stokes theorem brings us from a 2D object, which is a surface, into a loop, which is on a one line. No, that is completely true, and there is no accident, and that's essentially the concept. It tells us, one, what is going on with the circulations, as we discussed, and the other one will tell us what is happening with the flux. Indeed, if there is no question, let's go with applications of these theorem. Okay. Now let's keep it here because we want to watch them and look at them. Okay. Do you remember that we had Maxwell equations? We had divergence of B equal to 0. Let us use the Gauss theorem. So we multiply both sides by the volume that we had. So we assume that we have a volume, and inside of this volume, the divergence of B is equal to 0. And we want to understand what we will get from this. So that is equal to 0. If you bring the integral from volume to the surface, we will get integral of B dot d sigma is equal to 0. So what does it mean? That the flux of magnetic field on a closed surface is equal to 0. Okay? Do you agree? Let's go with the other one, divergence of E was rho divided by epsilon naught. Again, we have the same volume as the other one, but here divergence of electric field is equal to rho divided by epsilon naught. Good. So it means that there are some charges maybe inside of that. There are charges inside this value. Okay. Charge means electric charges. And remember, that was electric charge density. So we can use the Gauss integral or the Gauss theorem, multiply both sides by volume. Then I will get rho divided by epsilon naught volume. I can use the Gauss theorem to bring the divergence to the surface, and that's on a volume of V, which is this volume of V, and that will be E dot d sigma. And the other side will be epsilon naught is a constant. It will be 1 divided by epsilon naught, integral of rho d tau. Can you tell me what is the integral of rho d tau? Is the charge density multiplied by the volume. What it will be the result? Exactly. It will be the total charge. So whatever is inside of this, so it will be the total charge of Q. So total charge. Okay. And then that will be Q divided by epsilon naught. So then I get another form, which is integral of E dot d sigma equal to Q divided by epsilon naught, which is the total charge. Which means that the flux of electric field on a closed surface is given is proportional to the charge, total charges inside of that. So if there is no charge inside, then that is equal to 0, which is beautiful. Remember, doesn't mean that the electric field is 0. It means that the integral of E dot d sigma is equal to 0 on the surface. So for example, you may have an electric field, which is going like that, right? And then you assume a volume here. What is the charge inside of that? The total charge inside of this is 0. And definitely integral of E dot d sigma is equal to 0. But this doesn't mean that electric field doesn't exist here. So definitely there is electric field here. But the flux, which means that E dot sigma, d sigma, here it will give you negative value. E dot d sigma, it will give you negative value because d sigma is like that. And here d sigma is like that. So it means that electric field, that d sigma here, they are parallel to each other, or they are in the same, the angle between the two is below pi divided by 2. Here is indeed electric field is like that, and the d sigma is like this. So essentially that is higher than pi divided by 2. So the result of these will be negative. The result of these will be positive. So it means that if you split the surface like half, this part provides you the positive sign, and this part will give you the negative sign. So it means that negative and positive, they will cancel out each other, and means that the total flux will be 0, which is true because there is no charge inside of that, but doesn't mean that the electric field also is 0. Okay, so you have to be very careful. When you have materials, remember, when we had materials, we did not write divergence of E is equal to rho divided by epsilon naught. For materials, that was divergence of D is equal to rho. Okay, and then you can use the Gauss theorem again, and you will get integral of D dot d sigma is equal to the total charge. Okay. So I will write them down in a more elegant form at the towards the end of this lecture.
Sir, there is a question.
Of course, Vijdan.
Isa Hamadi says, can we say Stokes' theorem is the extension of Green's theorem to three-dimensional Euclidean space?
I'm not familiar with I'm not familiar with the Green's theorem in that way that that Isa is telling, because we have Green's theorem, but the Green's theorem that I know, they are different. They are telling something else. Okay, Isa, can you write me down in what you mean, or you can provide me some references that I can learn about that? Okay. But I know Green theorem, but I don't know this Green theorem that he's talking, or she's talking about that. Okay. Should I go with the rest? There's no further question?
There's no further question. You can
Okay.
continue.
Okay, thank you. So we use the Gauche theorem and now to bring two well-known integral Maxwell equations into the integral formalism. Now let's do the other equations that we deal with. So in order to write that, so remember that we had Stokes theorem. What was the Stokes theorem? Was a curl of a vector dot d sigma, and that was a surface, is equal to integral of that vector dot product of dr on a circle or a closed loop. See, and remember that was a surface, is a surface, open surface, and here you had the loop. That was C perimeter that you had. So that was Stokes theorem. Now, let's look at the Maxwell equations. Let's look at the last two equations. Curl of E was equal to minus derivative of B with respect to time. Okay, I can use the Stokes theorem, assuming that you have a circle like this, and you do the integral of curl of E dot product with d sigma, and then that is equal to minus integral of B dot d sigma. Okay, so of course that's a derivative, that's an integral, but one is on time, the other one is on the space, so you can swap them together. You will get the full derivative, because then we know that the coordinate is not function of time, so you do the integration there. So you have d dt of integral of B dot d sigma. Okay, what was that on a surface? If you remember, that was a flux, but the flux on that surface, so it means that is an open surface, so that's a normal vector, and then I'm calculating what's going on with the flux of magnetic fields through these surface. Okay, and I can use the Stokes theorem to bring this integral to a line, so bringing it to the loop that you have it. So that will be integral of E dot dr on a loop that you had, equal to minus d dt of the flux, or I have to be careful, magnetic flux. Magnetic flux was integral of B dot d sigma on that surface that was created or is created by the loop. Okay. Interesting. So it means that integral of E dot dr is equal to minus time derivative of the magnetic field flux. Okay. Oh, let's call it, just to not get confused with that's a flux. So means that if I have a loop, remember that's look like a wire that I'm making a loop. Okay. That's a dr. If you have the magnetic field passing through this, and if the magnetic field is constant, so means that the flux that is passing through this also is constant, then it means that there is no electric field created on the loop, on the circuit. So there is no electric field pushing the electrons around, okay? Of course, it goes in the opposite way. Okay, is that clear? However, whenever the magnetic field flux is changing upon the time, means that f of magnetic field is a function of the time, means that this magnetic field, which I showed with red, now is changing upon the time. Either the magnitude is changing or the orientation is changing. For example, if you have a magnet of N and S, you are moving up and down, then it means that the BT is changing, okay? Then upon this, you will create an electric field on the loop, which this electric field is against the changing of the flux, okay? Which is going with the minus sign here. Interesting, okay? That's what we call it, the Lenz, the minus sign comes from the Lenz law, and we call this the Faraday's law, okay? Wonderful.
Sir, there's a question.
Oh, how does the partial derivative changes to, because I'm doing the integration. I'm doing the integration on dx and y, okay? That
And
will,
Asa has also replied.
okay, I will keep the Isa's question for the end, if it's okay.
Yeah, you can continue then. There's no more questions.
Lovely, thank you, Vijdan. So now let's go. That was the third Maxwell, third equations of Maxwell that we had. We had another one, which was, let's consider for the time being in vacuum. Curl of B is equal to mu 0 J plus mu 0 epsilon 0, the time derivative of electric field, okay? That was another Maxwell equation for vacuum. We assume that we are working with vacuum. Again, I assume that we have a closed loop, and we have a surface which is created by that. And that's a closed loop of C, and the surface is given by S. Now I do integral of curl of B dot d sigma, which is equal to integral of mu 0 J plus mu 0 epsilon 0 time derivative of E dot d sigma, okay? So I can use this Stokes theorem to bring this integral from the surface to the loop. Again, it will be integral of B dot dr on the closed loop of C. And then on the other side, what I will get integral of mu 0 j dot d sigma. And then I have the other term, which is mu 0 epsilon 0, with the same fashion that I say it will be a full derivative of E dot d sigma. And these two, they are on the surface of S, which is the surface of S that we have shown. Mu 0 is constant. It will be mu 0 integral of j dot d sigma. And the other one will be mu 0 epsilon 0. And that is magnetic field flux. So it will be d dt of flux of electric field. Sorry, say magnetic. And what is that? J dot d sigma. So the current density multiplied by the surface, that will be the total current passing through surface S. Okay, so then I get mu 0 I plus mu 0 epsilon 0 d dt of flux of electric field through the surface S. So that is what I get as what we call it, the Ampere's law, with the correction that we have from Maxwell. Lovely. So that's the force equation of Maxwell. Assuming that there is no flux of electric field for the time being, we assume that the electric field is not function of the time. Okay, and if the electric field is not a function of time, then that term will be equal to 0, and then I will get integral of b dot dr equal to mu 0 I. And for example, I can assume that I have a wire. This wire has a current which is going, let's say, in the z direction. Then I want to calculate what's going on with the magnetic field. I can consider a circle with a radius of r. And since by doing the rotation, you will see that the magnitude of magnetic field will be constant on this circle, then you assume that B is constant here. But and the direction, it will be on the loop essentially. And then the result of that will be integral of B in the direction of dr, which is the angle is 0. So then if you do the integration on the entire loop, you will get 2 pi r. If you assume that that's the radius, then you will get mu 0 I, which is the total current that is passing through. And indeed, from here, you will get the magnetic field is equal to mu 0 divided by 2 pi I divided by r. And if you consider the direction, then that will be into the direction of theta hat, which the theta hat is in that way. Okay. So just to finalize, we had 4 Maxwell equations. Divergence of E is equal to rho divided by epsilon naught. The integral form from the gauche, it provides us that E dot d sigma is equal to total charge divided by epsilon naught. Divergence of B was equal to 0. And then from here, you will get the total flux of magnetic field in a closed surface. Remember, that's the closed surface is equal to 0. Curl of E was equal to minus time derivative of B. And from here, what we got integral of E dot dr is equal to minus d dt of flux of magnetic field. And curl of B is equal to mu 0 j plus mu 0 epsilon 0 time derivative of the electric field. Remember, those are for vacuum, okay? Maxwell equation for vacuum with charge and current densities. And then we got integral of B dot dr is equal to mu zero total current plus mu zero epsilon zero d dt of flux of electric field In electrostatic, electro and magnetostatic, the time derivatives, all of them, they are equal to 0. This is what you deal usually in fundamentals of physics 2, which you study electricity. So those are the integral forms of the Maxwell equation that you may face. So now let's go with questions, and then we will go with a couple of other theorems. Is there any question?
Yes, Mr. Muhammad Abdulaziz, I have a question. If you take a look at it, it's better because it's by some equation.
Okay. So, sir, I asked a question. I think I could not deliver the point clearly. No voice. When you did the cross product of these function, okay, we cross dr, you wrote something like this, that is Muhammad, is it possible that you look at the notes and you may write me an email, okay? You may write me an email about that and just check the note. Maybe I have done a mistake. It's very likely sometimes I do that. And tell me, okay? I'm sorry, because it's not really clear to me. Oh, thank you. So Shania Nouri is asking which part of Maxwell call it polarization and why? Polarization, do you mean the polarization of electromagnetic waves? If you call the polarization of electromagnetic waves, it's the freedom that you have in choice of the electric or magnetic field oscillation. So if you consider EM field, which I'm not teaching electrodynamics, I'm mathematical physics, but there the electric field, of course, is a vector. Magnetic field is a vector, but if you assume a wave that is propagating, well, in vacuum they are orthogonal to each other, and then they are orthogonal also to the propagation direction. So the choice that you have in choosing the electric field, which is going to be in a plane, we call it a polarization. If you mean another polarization that we have it, and that's related to how the electric field and magnetic field, they act on material, then we have another word named polarization. It is the degeneracy that physicists we have. And that word of polarization is associated to the way that we can polarize materials. We means that we can move the electrons inside of the material, and we create dipoles, and we call these also polarization. So, well, if you want, I mean, I can describe this in a better way later on. Okay. If there is no question, let's go with the green theorems. Now,
Excuse me, maybe she means which part of Maxwell equations is polarization, and I think it's no part of Maxwell equation named polarization.
oh, no part.
For example.
Yeah,
Yes.
yeah, there is no polarization.
Okay, thanks.
Okay, of course. Now let's go with the Green's theorem. Okay. Green's theorem essentially is really the basic for electrodynamics, because without that you cannot do the green functions. You cannot calculate some finding potential or electric field in a certain given places. So it's really important to learn the Green's theorem. So the Green's theorem all starts from two equations. Let's write it down. What is happening with the divergence of scalar multiplied by gradient of a scalar. Okay? So remember, what's that? Can you type it for me? Is it a scalar or a vector? You can type in the Q&A. Gradient of G, is the vector or scalar? Lovely, is a vector. So then I can determine what is happening with the divergence of a vector, which this vector is created by scalar multiplied by a vector. Okay, how do we do that, guys? So that means that I have the derivative, I do the calculation for x, is the derivative with respect to x, or let's write it in the way that we usually do. So derivative with respect to x of f, the x component of the gradient of j. So that's the x component of that, plus derivative with respect to y, f y component of gradient of g, plus derivative with respect to z of f z component of these. All right, good. So what is happening with the derivative of two functions? Because that's a scalar quantity, that's again a scalar quantity, there's a scalar quantity, it's a scalar quantity, and etc. So you have the derivative of two functions. It will be derivative of first function times gradient of g, the x component, which will be gradient of g x. Then we have the second one, which means that you have f, the derivative of x of gradient of g, the x component. And the same way, we have gradient of f with respect, derivative of f with respect to y. And then we have gradient of g, the y component, plus f derivative with respect to y of gradient of g, the y component, plus derivative of f with respect to z, gradient of g z, plus f derivative with respect to z, gradient of g, the z component. And if you do the calculation, that will be derivative of f with respect to x, derivative of g with respect to x. Then that one will be f. That will be second derivative of g with respect to x. That will be f y, g y, f second derivative with respect to y of g, and f z, g z, second plus f second derivative of g with respect to z. And if you cast them together, you will get derivative of f with respect to x, derivative of g with respect to x, plus derivative of f with respect to y, derivative of g with respect to y, plus derivative of f with respect to z, derivative of f g respect to z. And then if I factor out f, then I will get derivative of x, derivative of y, derivative of z of g. So this means that you have gradient of f dot gradient of j. This is what we have. And the last term is f Laplacian of g, if you recall. Good? In part of one, derivative of gradient of g must be written. Well, yes, I have written that one, right? So indeed, divergence of f gradient of g is indeed gradient of f dot gradient of g plus f Laplacian of g. Okay? Good, right? So we have, if you replace g by f, then this identity becomes divergence of f gradient of f is funny, right? Is equal to gradient of f plus f Laplacian of f. Interesting. Good, guys? Lovely. Now, let's take the integral. I consider that I have this function, and I can even simplify this. That will be gradient of f, the dot product of gradient of f. I will get gradient of f, the magnitude power of 2. And this one is f Laplacian of f. Okay? I can consider this function, which I assume that this function is well behaved, means that you can take the derivatives in a volume, and I integrate this on a volume of v or d tau, and then I will write it as divergence of f gradient of f d tau is integral of gradient of f power of 2 d tau plus f Laplacian of f d tau and a volume of v, volume of v, volume of v. And that's a volume of v, and the surface is given by derivative of f. I can use the Gauss theorem, bringing these to a surface that will be integral of f gradient of f dot d sigma on a surface is equal to integral of v gradient of f, the magnitude, d tau, which is a volume, integral of f Laplacian of f d tau and a volume. Okay? So, do you remember that d sigma was given by n dA? And usually what we write is, we write as f gradient of f dot n dA. So we get a formula which is integral of f gradient of f dot n. Some people, they write it even as derivative of f with respect to n. Remember, that's identical to that one. In some book, they write it in this way, is equal to integral of gradient of f magnitude power of 2 d tau plus f Laplacian of f d tau. This is, I will call it green theorem of number one. Okay, it is not in your book, but it's very, very useful in electrodynamics. Why we are doing this kind of calculations in electrodynamics or in physics? Laplacian is very important. Usually you have Laplacian of phi either equal to 0 or is equal to a constant. You will get usually these kind of things, and then you have a phi at boundaries, or you have the derivative of phi at boundaries. And we use the green theorem to link Laplacian to what is happening at the boundary. Okay, and usually we have several different kind of boundary condition, the Dirichlet, the Neumann, or mixed boundary condition, which is what electrodynamics essentially is based on that. So that was a green theorem of number one, which is very useful sometimes to show the uniqueness of a function. Let's go with the green theorem, the main green theorem that people they use it, and green theorem, or the main one, which in the book also, in your book is written, and also we are using it them clearly in electrodynamics, and I will give you some example towards the end of lecture tomorrow. So tomorrow we will be closing the chapter 1 completely. And how we can get the other green theorem, or the main one? Do you remember that we had the divergence of f gradient of g? The result was gradient of f that gradient of g plus f Laplacian of g. What happens if I swap f and g? So what does it mean? That what is happening if I write divergence of g gradient of f? It means that that's going to be gradient of g dot gradient of f plus g Laplacian of f. Let's subtract these two together, okay? Let's subtract them. If we subtract them, there is no difference between this term and that term, so they will cancel out each other. So what I will get the divergence of f gradient of g minus g gradient of f equal to f Laplacian of g minus g Laplacian of f. Okay. Again, I will consider a volume of v with a surface of derivative of v, and now I will multiply both sides by d tau, and I will use the Gauss theorem, and the Gauss theorem will tell me that I have the divergence on a volume becomes f gradient of g minus g gradient of f on a surface is equal to f Laplacian of g minus g Laplacian of f on a volume. Okay, and as I say that d sigma, usually we write it as n dA as we described previously. Remember that is on the surface integral, and that is on a volume integral. So one can write this as integral of f gradient of g dot n minus g gradient of f dot n dA is equal to integral of f Laplacian of g minus g Laplacian of f d tau, which is on the volume. Some book, as we described, they write this as a directional gradient or derivative of g, and they write this also as derivative of f in the direction of n vector. Okay, some books they write it in this way. We call these green theorem, or the main green theorem. Again, why this is important? Because it tells you how to link Laplacian to the boundary condition on a surface, and we will be using this during the next lecture for driving some equations. Is there any question, guys? If not, then I will stop here. And
Sir, before you stop the recording, I want to share something with the class.
yes, sure, please.
Yeah, I want to remind the attendees that the deadline for the first assignment has been extended to 17th August. And those of you that cannot join the classrooms can send their assignments to the moderators of the classroom by email. You can find the emails on the KMS website. Thank you.
Of course, thank you very much. So if there is no question, I will stop the screen sharing, and I will stop also the YouTube channel as well. And that one.